and welcome to Cherry Pie Math. This video is going to introduce experimental versus theoretical probabilities. Before we get started, you do need to know how to make a probability, like the basics of it, and you need to be able to convert from a fraction to a decimal to a percentage and back. So just kind of to review a little bit, kind of going back to when I said basics of making a probability, let's arrange these from least to greatest. I'm going to change this to a white marker. Here we go. So let's say we have flipping a coin and getting heads. That would be 1 out of 2 because there's 1 out of 2 possibilities, right? Or 50%. Drawing a heart from a standard deck, that would be 1/4 because there's 4 suits and heart is one of those suits. That would be 25%. Drawing a blue marble from a bag where 5 are blue and 3 are white. So that means there's 5 blue marbles and there's 8 total marbles. Be careful to add those two. And I actually don't know that one off the top of my head. Let me grab my calculator here. 5 divided by 8 is 62.5%. Rolling an odd number on a 6-sided dice. That's 3 out of 6 options, or 1/2. So we actually end up with the same as A, because you still have 1 out of 2. If we're going to roll a nat 20 or natural 20, I don't actually know if that was the right slang here. Anyway, on a 20-sided die, that would just be 1 out of 20 because on a 20-sided die, there are 20 numbers and 20 is one of those numbers. And that percentage would be 5%. And then picking a student that plays sports at a school where 300 out of 500 play a sport. So that's 350 out of 500, which would be 350 divided by 500 is 70%. Okay, so if I was to arrange these from least to greatest, I would obviously start with E, and then I'd have B, and then I'd have A, and I'd have D, and I'd have C, and I'd have F. We calculated each of those possibilities by doing the number of successes over the number of possibilities. And that's basically how you calculate any probability. It's the amount of times that you'll have a success out of the number of possibilities that exist. So theoretical probability is what we just did. Theoretical probability is just that. It's the number of successes over the number of possibilities. But it's theoretical. It means that it represents the expected ratio. But it's just theoretical. So let's pretend we're flipping a coin. So the probability of flipping a coin and getting tails would be 1 out of 2, right? Because that's one option out of 2. So if I was to do this 10 times, and I'm basically changing this to out of 10, that means I'm multiplying it by 5. So I would expect to have 5 tails, and that would be my theoretical probability. Theoretical probability. If I was to do it 20 times, same idea. It would just be 1 out of 2. So if I was to make it out of 20, it would be 10 out of 20, and that would be my theoretical probability. I would expect to have 10 tails. So let's do an example of this. So let me split this screen here. Here we go. So I'm going to flip a coin, and we're going to see what happens. So okay, we did it. Yay. Okay, So our hypothesis was that if we flipped a coin 20 times, you'd get 10 tails. So let's count the amount of tails. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I had 11 tails. So that actual percentage would be 11 out of 20, which if I divided it out would be... It's funny because when you're a math teacher, everyone expects you to be able to do this math in your head, but like that's why we have calculators. Anyway, it would be 55%. It ended up not being exactly 50%. We got close. And in fact, if we had only done it 5 times, we wouldn't have gotten any tails at all. So that's what happens with theoretical probability. It does not match. We did not match the original theoretical probability that we had before. Did that change the theoretical probability? So now that we've done the experiment, does that change your opinion that it's actually 1/2, or will the probability still be 1/2? Just think about that. Does that change anything or not? And I guess that's why we call it theoretical probability. And then we have what's called experimental probability. Experimental probability is the actual percentage or ratio/percentage that the success occurred. So what we were looking for. In this case, we were looking for tails. Our experimental probability was 55%. Our theoretical probability was 50%. They were pretty close, but it wasn't an exact match. So then why do we even need theoretical probability? If we have experimental probability, why do we need theoretical probability? Why do you guys think? So I guess some things to remember, because I'm not going to answer that question for you. I want you to think about it. Why do we need theoretical probability? Why is that useful to us? Why not just use experimental probability all the time? So theoretical probability helps us predict the outcomes, but the probability is that it'll probably happen like that, but not exactly. And the experimental probability will probably be close to that theoretical probability, but not always. When I was teaching this to my students, one student said that her aunt got like Yahtzees like 6 times in a row, and she asked me to calculate the probability of that. That doesn't happen, right? But it does. Like every so often there's this miraculous thing where they always get Yahtzees, where it always comes out to be just this crazy success that defies the odds, that defies our theoretical probability. So they usually match-ish, but not always. That's the cool thing about living in the real world, and that's one of the things about probabilities. That's why betting, and like sports betting especially, is so dangerous, is because things happen. The world is different than what you would theoretically think. Anyway, I hope that helps to kind of explain the difference between experimental and theoretical probabilities. And remember that they do not always match, but they should be pretty close. Okay, good luck.